Okay, welcome everyone. What is today? Wednesday, 5 p.m. Is everybody able to hear me okay? Alright, at least one person. Okay, good. So, let's get started on Kinematics2D. I'm going to do a typical problem of 2D, the simplest one ever. And the reason for this is because the method that we're going to be using, as you will see, is very similar to the method in 1D. And this one can be also applied to all the problems in 2D. And then hopefully later today we'll do another type. If not, we'll do it on Wednesday next week. And then you should be able to complete all the other problems. So, Kinematics2D or projectile motion is exactly the same as Kinematics1D in freefall, except now instead of throwing an object up and down, we're going to throw it with a particular angle. That's all. The equation that we know and have been using are going to be exactly the same ones, which is good news. So remember, we've seen two definitions so far. The basic definition of kinematics that allows us to derive all the equation of motion for constant acceleration. The first definition of kinematics is the acceleration is equal to the derivative of the velocity with respect to time. And the second definition of kinematics is a definition of velocity. And if you're doing 2D, you replace this by r. So the change of position with respect to time. Those are the two basic definition of kinematics. From those, as you've seen on the lecture, you can derive all the equation of motion. And the one that we've been using are those guys. In 2D, same thing. As you've seen on the lecture, we can derive all those equations in both the x and the y. And there will be one more, which is the last equation that will allow us to relate the position x and y with respect to each other without involving the parameter time. And then the third definition that we've learned is the definition of freefall, which states three things. First, that the acceleration is constant. And for good luck, we write it as g. Second, that it has a specific value of 9.81 meters per second squared. And third, that its direction is down. This definition of freefall also applies in projectile motion or Kinematics2D. Okay? So, let's take an example where we have a ground, and instead of throwing the ball up and down, we're going to throw it with an angle, which means that the motion is going to look like this. But motion in 2D or projectile motion is always a parabola, same as the position versus time in Kinematics1D. It never goes in a straight line. The velocity may, and the acceleration may, but the position is always a parabola. So in this case, we're plotting x versus y. So x versus y in 2D has the exact same behavior as y versus t in 1D, a parabola. So instead of throwing an object up and down like we did in 1D, we just give it a particular angle. By convention, this angle is usually defined from the horizontal direction. So let's plot some of those velocity vector. If we plot, remember, position versus time, if we take the derivative, because of the basic definition of kinematics, tells us that the slope of a position versus time graph or position versus position graph refers to the velocity, just because of basic calculus, which means that we can plot our velocity vector at any point by drawing the slope. and the slope of any point will be our velocity. The initial velocity at t is equal to 0 will be our initial velocity. This one. But as you can see, since velocity, acceleration, position are vectors, in 2D they're going to pick up two components, the x component and the y component. So that's where we're going to use everything we know about vector decomposition. So if I zoom at the initial time or position, and I draw my velocity vector, this velocity vector can be decomposed as any vector into two. It's x and it's y. Since direction is given from the x-axis, so we've recognized our usual right-angle triangle, and therefore from basic vectors, we know right away, if we're given v0, that the x component is nothing else but v0 cosine alpha, and the y is going to be v0 sine alpha. Okay? This is going to be our v0 x and v0 y. Obviously, the velocity vector changes, at least its direction. Direction is here, then direction changes, then changes, then changes, then changes. Same as 1D, we have an apogee, which is the highest point. At this particular point in 1D, the velocity in the y direction was 0. This doesn't change in 2D. At this particular point, say A, the y component of the velocity is also 0. So it's also something that we can use as we solve for projectile motion. However, our object is still going left and right. So as you can see, I still drew a velocity vector. If this vector was 0, then the object would just drop. So in 2D, we have to be careful that we only remember that the y component of the velocity is 0 at point A, or apogee, but the x is not. Okay? So the behavior of the y component of the velocity behave exactly the same way as in 1D. As you go up, the magnitude will decrease until you reach apogee, and after apogee, the magnitude will increase again, and the direction will flip. And this is caused due to the fact that it was a free fall, because the acceleration was against the velocity initially. But let's look at the x component. What do you think the x component of the velocity will be affected as we go from point O to point A to point B, which is the point right before it hits the ground? Is the x component of the velocity is going to be affected by the acceleration which is perpendicular to it? Excellent. Absolutely. That's the beauty of kinematics and projectile. We can separate the two dimensions and treat them independently. So the y component of the velocity will be subjected to the acceleration, same as 1D type of kinematic. But the x component, since the x component has been chosen to be a line or x-axis, and this x-axis is perpendicular to the acceleration, this acceleration only affects the y component. It does not affect the x component, which means that ax will be 0. Therefore, the change of velocity in the x direction will be a constant. Okay? Hence, the x component will always stay the same. So this component here should be the same as this component here, should be the same as this one, should be the same as that one, and etc. at all time. Okay? All right. What else can we learn from this simple diagram? We can see similar symmetry as in 1D. Remember when we investigated the cookie frog, the velocity that he has right before impact in magnitude is exactly the same as the initial velocity, because it used to take the same amount of time to go up as the one to go down. Therefore, if we know the v0 initial, we know that its magnitude, it will be exactly the same as the velocity right before impact. as you input the dimension in the x-axis, the same behavior will take place. The y component of v naught will be exactly the same in magnitude as the y component of the velocity right before impact. But the direction will be opposite. So you can use that symmetry if you want to. If you don't see it, the equation will confirm it. But if you want to use that trick, you want to make sure that there is a symmetry. For instance, in this particular case, where the plane is not level, obviously the symmetry is broken. So the initial y component of the velocity here is not the same as the y there. It will be the same right here, which is a random point. So be careful that if you want to bypass some of the mathematics and equation by using symmetry, that the symmetry is actually real and present. All right. So we're going to use the exact same technique as in 1D. The first thing we need to do is obtain the set of equation that is specific to our situation. Let's imagine that we're given v naught and theta. So let's say v naught is 3 meters per second and theta says 30 degrees. And we want to know everything about this motion. For example, we want to know the maximum height, we want to know how long it takes for us to get there, then we want to know how long it takes for us to go all the way to the impact or right before impact, and we're interested in seeing how far we can find the object at B. So how far we can throw the object. Those are usually common questions that we will have in 2D. So first thing we need to do is, again, use the same method as 1D to simplify our equation. Since we now have 2 dimensions, we need to take those generic equations and apply them to both the x and the y direction. So we have double work to do. We have to do it separately. Let's start with the easy one. So remember, those x's are generic x. As we rewrite the 4 equation in the x direction, we're going to replace or keep those 2 x's. But as we go and rewrite the y direction, then we're going to replace all the x by y's, same as before. So we know that the projectile motion is the same as free fall, therefore the acceleration is constant, is equal to 9.81, and its direction is down. Therefore, as we look at those equations in the x direction, what simplification can we make due to the definition of free fall? That is there any term that we can set equal to 0 in the x direction? There is 3 kinematic variables: position, velocity, acceleration, and time. Is there any of those 4 that we can get rid of due to the definition of free fall? Excellent, Michael. There is obviously no acceleration in the x direction. Therefore, how can we express this mathematically? Which variable can we nuke? Excellent. All the a's are 0. Those refers to ax. And these are vx. So all the ax goes away. Nice. Look at the first 2 equations. Are they the same or are they different? Yeah, I'm not even approaching the knot just yet, but we'll get there. The knot value will be, again, dependent on the location of your origin, right? So same as 1D. But before we get there, look at those 2 first equations. Are they the same or are they different? Can we just use one of the 2, or do we need to keep both? And if we can get rid of one, why is that? I don't know. You tell me. What would it depend on them? So if I set x naught to 0, then the first equation becomes x equal to vt, and the second becomes x equal to v naught xt. Are they the same equations? Is the first and second equation, just look at them. Are they the same equation, or is there a little bit of a difference? Tyson suggests to get rid of the second one because the initial v is 0. Be careful, the initial v is not 0. If the initial velocity was 0, we wouldn't go anywhere, right? Plus, it was given to us as 3. So v naught is not equal to 0, which suggests that by applying vector, v naught x is not 0, v naught y is not 0. Cynthia suggests they're not the same because v naught x is not equal to v. She's right. I forgot the little label. Everything is x. So the question is vx equal to v naught x? Right? If they're equal, those two equations are exactly the same. Are those two equal? Let's remind ourselves about the definition of free fall. Yeah, excellent. Free fall said the acceleration is only down. There is no acceleration in x, which means that ax is equal to dvx dt, which is equal to 0. Hence, dvx is equal to 0. Therefore, v final minus v initial is equal to 0. Therefore, vx is equal to v naught x. That's what we just talked about. The x component of the velocity remains the same. Therefore, those two terms are the same. So those two equations are the same. So we don't need to keep both of them. We can just keep the second one or the first one. You decide. Okay? This is actually confirmed right here by the third equation. So everything is consistent. Exactly. Gravity doesn't act on it, therefore it doesn't change. The third equation now becomes the second, confirms what we talked about, which is that the x component of the velocity doesn't change. Which is also confirmed by the last one. Now the last one is a bit trickier because there is a square, which means that mathematically we have more than one solution. But in physics we only keep one, which refers to the second equation. So really, as we apply the definition of free fall to our set of 4 equations, and we try to simplify them in the x direction, what do we get? Only 2 of relevance. The x component of velocity at any time is equal to the initial one, which by using vector is v naught cosine theta. And x is equal to x naught plus v naught t. And again, you can use, v naught x. You can use v naught x or you can use vx because we just saw that they're the same. Right. Nice. So 4 becomes 2. Now, what about the choice of the origin of our coordinate system? Is our choice going to allow us to simplify those equations a little bit more? In this particular case, I have chosen to pick my coordinate system x and y at my initial time and initial position. So at point O. Excellent. I'm still only dealing with x, so I'm only concerned about x naught just now. Perfect. No, excellent. Good. So with this choice of coordinate system and just using basic definition of free fall, we have now a set of 2 very, very easy equations. Those are the only equations we can use in the x direction. Excellent, Jimmy, as well. But again, I'm only doing x for now. But we're going to reuse what you both said as we're doing the y. Okay? So x usually is easy. 2 steps. Use the definition of free fall to get rid of all the acceleration term, which resumes those four equations into two. One confirms that the x component of the velocity remains constant and is equal to the initial x component, which is equal to v naught cosine theta based on using our vector skills. And that if we set up the original current system at the initial time and initial state, then x naught can go away as well. Nice. Let's do the exact same thing with y. And this one is very similar to what we've done in 1D. First, we're going to change all our x's with y. But here we have to be careful. Not just the position, also the velocity. Common mistake. People decide not to use their x and y label, and then they mix them up. So make sure that you always add your labels. All right. Same as 1D. Is there any equation that we can get rid of, and why, as we look at our four equations in the y direction? So we're going to follow the exact same method as before. Excellent. As we've seen last week, over and over. First one out, because the first one can only be used if the acceleration is 0, and since we're looking at the y direction, we know the acceleration is not 0, but it's constant, has a magnitude of 9.81, and its direction is down. Good. What else can you infer from the definition of free fall? Specifically, the fact that the direction of the acceleration is down, and using the choice of our coordinate system, specifically the direction of y. Excellent. We can replace all the a by negative g. Negative 1/2 gt squared. So same as before. Nothing new under the trees. The only new thing and very important thing is the subscript. We need to keep track of our subscript. That is, this v is not the same as this v. Those are x's, those are y's. So we cannot mix them up. What else? What else can we nuke, and why? Again, go back to your notes. Same method as 1D, which was suggested by Henry and Jamie earlier. Excellent. All our initial position will be 0 due to the choice, our choice of the origin of the current system. Good. So we can nuke all those little guys. What else? Okay. Perfect. So it looks pretty similar to last week. The only addition that we need to add is this. And usually people suggest strongly to include them into the equation so you don't forget. Especially if you don't bother writing the component. Because if people don't, then they will end up mixing those variables with each other. So one way not to forget is to substitute those values directly into your equation. Hence, the final equation in both x and y will be Vx is equal to V naught x is equal to V naught cosine theta. X is equal to V naught cosine theta t. And in a y, same as in 1D, we only keep 3. Y is equal to V naught sine theta t minus 1/2 gt squared. Vy is equal to V naught sine theta minus gt. And V naught Vy squared is equal to V naught sine theta. Both are being squared, minus 2gy. Done. Now we have all the equations for us to answer any question that may be thrown at us. And those equations are specific to the choice of our coordinate system. which is usually the one people pick in projectile motion. They pick the origin, they pick the center one, y up positive, x positive towards the left, unless you're going, towards the right, unless the motion is going towards the left, and they pick the origin at the initial time and initial position. All right, any questions so far? So I hope the WI folks have taken good notes, because those are the steps that you need to write out explicitly. Good question from Michael. How come you prefer to look for aspects of the equation that we don't need to make them smarter, rather than creating a list of what you're given and what you need to? Absolutely. The reason why I go in this order is because I want to cover all the bases for any question that may be asked afterwards, rather than identifying what is it I need to know and only identifying the equation that I need. So it's just a more general approach. I will follow the exact same approach with Newton. Again, for this, the reason for this is to be systematic, to have the general method off the bat, so we master it. And then you can answer any question that may come to you on the fly. But you're right. If you realize, okay, I'll really only need that equation, then I'm only going to justify the simplification of this equation. If you're in the WI section, I'll take that. I'll take that. Okay, just don't make sure you don't forget any equation justification. If you realize later on, oops, I needed an equation, and then you forget to go back and justify a simplification, then you're going to lose points. If you are in a WI section. So again, the reason why I'm doing this is I'm going to do the same thing in Newton, and you will have the exact same question. You're going to ask me that when we're going to start Newton, why do you bother with that equation, since we don't even need it? And the answer that I will give you is, we don't need it now, but a week after, as we're going to introduce friction, we are going to need it. So we might as well take the habit of just get it out of the way, so that when we need it, bang, it's right there. Okay? Good question, thank you. Any other questions? So I'm going to erase the board on top to make a little bit more space and start investigating those common questions. First one is, let's try to figure out the height, the maximum height, the apogee. Which equation do you think we could use to figure out the maximum height? Hang on, let me label this equation just so that we are clear. Equation 1, equation 2, 3, 4, and 5. Oh, I could use Henry's method. Oops. Put everything back. Woo! Huh, it's funny. Okay. So I see equation 3, equation 1, equation 4. Oh boy. If we're looking for the maximum height, which variable are we concerned about? Excellent. Y. So we need an equation that has Y. How many equations has Y? Or which ones? Equation 3 has Y. Anything else? Equation 5. So we could technically start with any of those two. So for us to make a decision, let's continue and watch all the other variables on the equation. Equation 3 has Y, which is what we're looking for, and has V0, we know V0, has theta, we know theta, G, we know G, but has time. So really, for us to be able to use equation 3 to figure out the maximum height at point A, we need to know how long it's going to take to get there. But we don't know that Therefore, let's leave it on the side and look for another alternative. Next alternative is 5. Excellent, Kyle. 5 has the y. Everything else is known, but now he has a vy in there. But we remember from 1D, as Kyle suggested, it's the apogee. Therefore, at A, Vy is 0. Hence, equation 5 becomes 0 is equal to V0 squared sine squared minus 2gy. Or y is equal to V0 squared sine squared divided by 2g. Bang! Obviously positive because A is above our x-axis. Perfect. See, just as easy as 1D. Piece of cake. Now, if we're interested, if somebody throws a new question at us and say, okay, now I want you to figure out the time it takes to get to apogee, which equation can we use? We could use 2, because 2 has time. But then let's keep looking all the other variables. We know V0, we know theta. Do we know x? X must refer to the x position of the apogee, or xa. Do we know the x position of the apogee or point A? If yes, then we can use equation 2. If no, then we have to move somewhere else. Do we know x, which is, remember, always between 2 points. Therefore, this x must be the x of this point, because we're going to apply this equation between point O and point A. Do we know the x component of A? Do we know this? Nah, we're toast. That's okay. Let's look for another one. Is there any other equation that has time? Yeah, 4 and 3. Can we use any of those two? Try go through all the terms and ask yourself, do you know everything else? Yeah, Kyle suggests we can use 4. And we use the same trick. V0 is equal to 0, which will allow us to obtain and solve for t, which is V0 sine theta divided by g. Nice. What about 3? Can we use 3? Do we know everything else? 3 has time. But 3 also has a y in there. What is that y referring to? Yeah. Which height specifically, Kyle? Yeah, the point of A. Do we know the y component of A? Really? We don't? Oh. Yeah, we do. We just did it. It's this one. This is the y component of A at apogee. See, that's why I wrote it at A, so we don't forget. Maximum height is the y component of A, right? Excellent. Yeah, now we're looking for how long is it going to take for us to reach apogee. So we could use equation 3 and substitute what we obtained earlier in equation 3. We will have V0 squared sine squared theta divided by 2g is equal to V0 sine theta times t minus 1/2 gt squared. That's a polynomial of second degree, right? We know how to solve for this. We've seen it last week. A times x squared plus b times x minus c is equal to 0. Therefore, we can use the quadratic. The solution for t will be negative b plus or minus square root of b squared minus 4ac divided by 2a. Obviously, this is a much longer option. And you're most likely, or may, since you're dealing with a polynomial, you expect 2 solutions for t, one negative, one positive. But remember when we mentioned last time, as you apply this to the apogee, what will happen is that the square root, or whatever is under the square root, will end up being 0. which means you're only going to get one solution in this case. And guess what? The solution is going to be this one. Exactly this one. Okay, so when you practice at home, make sure you use them all and confirm the same answer. For a test, obviously, we want to follow Gal's leadership. Take number 4, bing bam boom, one line. Okay, so please review quadratic. It's going to come back over and over and over. That's high school algebra. Perfect. How is it so far? Just as easy as last time, yeah? All right. Practice will fix that hesitation. Now, next question. How long does it take to hit the ground? Point B. You have two options. Either you give your shortcut, or you use whatever equation you think is best. We're interested in figuring out the time that it's going to take to reach point B, which is the instant right before it hits the ground. So to go from here to here. Okay. Carl said, we know that Vy at this point is the same as Vy naught. Excellent. Which means that you're going to be able to use which equation? 5, 4? 4. All right. Excellent. If you do this, what are you going to get for t, though? Try it. It's a good idea. Let's see if that helps. If you replace Vy by V naught y, which is V naught sine theta, what are you going to obtain for t? Just by looking at it. Do it. Go for it, Michael. There is a lazy and silly, well, I don't know if it's silly, but there is a lazy way to do it. So if you can figure it out, let us know. Exactly. Excellent. That's using symmetry. Excellent. So that's the first and lazy way, but the clever way. We know, same as in 1D, it takes a similar time to go up as it takes to go down, as long as the ground is level. Symmetry is there. Therefore, you can just take this value, multiply by 2. Done. Exactly. So t to get to B is twice t to get to A. Hence, twice V naught sine theta over G. Could you clarify your question, Michael? The equations we just saw them, right, for this type of problems. Those are the same 4 as last time, right? Is that what you're asking for? Yes, Michael. If the surface wasn't flat, the symmetry will be broken. Okay. Yeah, same exact 4 equation. Right? We used the exact 4 equation when we started to deduce those easy equations, simplified ones. But I want to go back to Kyle. Did you obtain this answer as you substitute V naught y for Vy here and solve for t? No, you didn't. What do you get? What is the answer you got? Oh, is that what we're asking, Michael? Is there different equation that we could use in case the symmetry is broken? If that was what you meant, nope. We can use the exact same equation. Those equations can be used even if the symmetry is broken. They're wonderful. Kyle, I'm a little bit worried. If you replace, as you said, V naught by V naught y, and you substitute in equation 4, how did you get t is equal to V naught sine theta divided by g? How did you get that? Can anybody do it? It's high school algebra. You can do it in your head. If you use that trick that you wanted to use, which was clever, substitute in equation 4, what are you going to get for time? I want to make sure this is clarified, because otherwise people might decide to use that trick later on and waste some time. it is actually a correct equation to use. What I'm trying to make everybody realize that the answer or the information we're going to get is not going to be useful, but it's still going to be true. So can you all do this? Follow Cal's advice, replace V naught by Vy naught, and substitute in equation 4. Then solve for t. This is basic high school algebra. What are you going to get for t? Close. Use the fact that the y component of the velocity at B is the same as the y component of the velocity at O, which we talked about earlier. Let's use that trick as Kyle suggested and substitute the functional form of Vy naught into equation 4. So make that substitution right here. Replace Vy by Vy naught and replace Vy naught by V naught sine theta by its functional form. You may get two possible answers. One over G? No. Algebra problem, Henry. 0.15. Could you give me your answer before you plug numbers? Just the functional form. So you obtain, so if you substitute V naught by V, if you substitute Vy by V naught sine theta and you solve for G, you solve for T, you end up with T is equal to V naught sine theta divided by G. Ooh, thank you, Kyle. I'm a little bit worried, people. This is high school algebra, maybe elementary school algebra. I'm a little bit worried here. If you substitute this, as Kyle suggested originally, into equation 4, then you have V naught sine theta is equal to V naught sine theta minus GT. Can you solve for t, please? Yeah, of course we get 0. Whew. All right. Does that make sense? Yeah, it takes 0 time to get to B. It's like teleportation. Remember, we're looking for the time it takes to get to B. And for this, Kyle was suggesting, let's use that trick, because we know that. Yeah, but the problem is, we can't use Star Trek tricks. So obviously we've got a problem. But obviously this refers to this point, which is one of the two legs of the symmetry. Kyle actually answered his own question. What else do you suggest, Cal? Instead of replacing Vy by V naught y, we should have replaced Vy by excellent. This is V naught y up. This is Vy down. So sure, they share the same magnitude, but they obviously have different directions. So as you suggested right after, Kyle, we need to substitute negative V naught sine theta. And as you do this, then you solve for t, and you end up with the same answer. So you are on a perfect track, but we have to be careful about our signs. That's why drawing a diagram is very, very important. Drawing little vectors is very important, because then we don't forget the signs. Okay? So in this case, we had two different approaches. The symmetry approach, twice the time we obtained earlier, or equation 4. Now, there is a third method. Is there any other equation we could use to figure out the time to get to B? Is there any other equation that has time? Yeah, of course, 3. Excellent. Can we use 3? Do we know everything else but T? Yep. Now, can you be a little bit more specific? That is, excellent. Thank you. Excellent. If we apply equation 3 between point O and point B, then everything that it is not carrying a knot refers to B. Therefore, this little bugger refers to B. And we know what the y position of B is. It's 0, just by looking at our graph. That's why, again, our diagram is the key. It will tell us information that we could use. Excellent. So we just set this equal to 0, bang, and we solve for time. You don't even need to use the quadratic equation because the C value is 0. And you will get, again, the same answer. So 3 ways to get to heaven. Okay? Perfect, perfect, perfect. Now, last question. How far are we going to throw the whatever we're throwing? That is, what is the coordinate of B in the x direction? We usually call this the range. So write that down. Whenever you're being asked for the range, it's the horizontal component of the landing point. Good question. Do we have the time that it takes to go to B? Have we figured that out yet? Mabel said yes, he had 0.31. Is it somewhere on the board, the value of the time to get to B? I believe you're correct because I've seen 0.15 earlier. Yeah, we did it right here, right? Remember? We use a symmetry. So we know the time it takes to go to B. So now that we know the time, which equation can we use to obtain how far the object is going to land, which is the range, which is also the x variable, right? Yeah, excellent. There is only one equation that has x, so there is no ambiguity for that one. So we can plug the t that we got here, poof, put it there, bang, get x using the second equation. Perfect. That's it. That's all there is. That's all there is. That's all there is. Now, if, for example, in this case, I led you with simple question in order for us to get more complicated one. For example, I started asking question about information about apogee. And since we had symmetry, we could deduce information easily with respect to point B. If I'm not that nice, and I don't ask you all those intermediate questions, the first question and only question that I may ask you, for example, so let me erase the board, maybe, please calculate the range. That would be the first and only question that you may have on the problem. Using the equation that you have, how would you do it? So again, if I'm asking you for the range, you know that you're after this. Therefore, you know that you need to use equation 2. The problem is, because that's the only equation that has x, the problem is you don't know t. So solve for t from which equation, Michael? Four. But if you want to solve for t from equation 4, you need to know Vy, which is okay. But it means you need to get Vy from somewhere else. That means you need to get it from equation 5. So that means we have to combine 3 equations. Right? We know that y is equal to 0, therefore we can solve for Vy. We can substitute that Vy right here, therefore we know the time, and then we can substitute the time right here, and we know the x. That will work. Is there any other method that you may see? And again, Kyle, let's imagine we don't know the time. We haven't done it. Let's imagine that that's the first question that you see on the problem. So we don't know 2v0 sine over g. Alan suggests use equation 3. Yes, much faster. We can bypass equation 4 and 5. Why can we use equation 3, Alan? I'm guessing to solve for t so that we can substitute it into equation 1, right? Excellent, yeah, because we know that further away where the ball is going to land, y is 0. Excellent. Good. So you can do it by step. And usually the intermediate step is often the time. Or here is the other method, which is I'm going to use the exact same technique as Alan, but in the different order. This is a diagram that represents the position x in terms of the position y. And I've made the claim that in every projectile motion, the trajectory is never a straight line, ever, ever, ever. It's always a parabola, which suggests that if I obtain the functional form of y as a function of x, it got to be a parabola, right? It got to be proportional to blah blah x squared plus blah blah x plus blue blue. And we know that there is a negative sign right here. Do we all agree? Do we have any of such equation here? Do we have an equation that relates y and x exclusively, without any time? No, we don't. However, in 2D, that equation may be very, very useful quite often. So you always will have the choice. Either you follow Michael's approach, which is to substitute and combine equation to say get Vy, then t, then substitute it back into x equation, or you follow Alan's shortcuts, which is to forget about 4 and 5 but focus on 3, solve for t there, and then once you get the numerical value of t, bang, you plug into x. I agree, it's a little bit faster, just one step faster. Or you derive it yourself and you keep it to use it whenever you want. How are we going to do this? If I have an equation of x with respect to time and y with respect to time, and I want to combine those two to obtain, as Alan suggested, y as a function of x, I have two options. Alan's approach, I solve for t in the y equation, substituting the x. However, this was an easy step because y was equal to 0. If y is not equal to 0, then that's a quadratic equation. So that's a pain in your collet. What about going the other way around? Yeah. Take equation 2, solve for t, and substitute it into equation 3. Instead of going from equation 3, solve for t, which in general will give us a quadratic, that's more work, and then substitute into 2. Let's use this method. If you take equation 2 and solve for t, you easily have t is equal to x divided by v naught cosine theta. No biggie. Now let's plug this in equation 3. Y, and we keep y not equal to 0 so that we have the general form, is not equal to v naught sine theta times this t, which is x divided by v naught cosine theta. So obviously the v naught disappears. And we only left with x times sine divided by cosine, which we know is tangent. And now we can go to the next term. Next term is 1/2 g times t squared. Plug the t, x squared. Let's not forget to square all the terms. And we end up with this. And this indeed looks like a parabola, with the negative sign that we want, so that it is indeed an inverted u, or n. And the constant term is y0, which in our case is 0. So just by doing a one-step algebra, you now have another equation on the u-belt, which allows you to relate x and y exclusively and entirely without having to worry about any time. And this is an equation that will be useful for you if you're not given any information about the time in the problem, and you're not being asked anything about time either. Usually what most people do is they use the two equations that they have obtained, simplified, and they go straight into expressing this, and then they use this equation for the whole problem. Okay? Any questions? All right. I want to, break time. Okay, so let's take a break. Then I'm going to do two more problems. The first one, I'm just going to lay it out and look at the initial condition. And the second one is the exact same problem, except we're going to break the symmetry. Therefore, the slope is going to be inclined. And with those three problems, you have all the tools to do everything else. Good. Let's take a quick break, and let's meet again. It's 5.59, so let's resume at 6.9. Wow, 6:10. I'm going to release the board. Okay, so is there any question that may have popped up in your mind during the break that needs clarification before we continue, and after I find my pen? Oh, here it is. Okay, so Michael is good. How about everybody else? All right. Okay, so let's look at another example. I'm just going to lay out the beginning, because that's usually a common source of error. So make sure you take good notes of this so that when you sit, it's for the case where you either start vertically, horizontally, or with an angle. So for example, you start from a tabletop and you throw an object like this. Or you, and some of you may recognize this, you start from a roof, and therefore, oops, there's a small house like that. How are you going to handle this situation? What is the big difference between, say, case A and what we just saw, which was like this? What has changed? And think initial conditions, because really that's the only thing that will be sticky. What is an obvious component that is different? Okay, so let's imagine that we are going to pick our coordinate stem at t is equal to 0 for all. So this will not change. Okay, now try again. First of all, we lose the symmetry. Yep. What else? Is there any variable we only know 5 variables: position, velocity, acceleration, time, angle. Is there any of those 5 that is different from case A to case C, the one we just did, and later on from case B to case C? Y are going to be negative, correct. Give me one more. Think initial condition. Excellent. Theta is going to be the one that will differ. Does everybody see this and agree with it? That in addition for the Y to change sign between case C and A and B, also the initial conditions are different. Specifically, the angle will be different. In this particular case, the angle is 0. Which means that since we know that cosine of 0 is 1 and sine of 0 is 0, V naught x will survive, but will resume itself to V naught, because cosine of 0 is 1. And V naught y will be 0. Hence, your equation will be dramatically simplified, which is nice. What can you tell me about the angle on case B? And I give you a hint right here. Draw the slope at t is equal to 0. Excellent. Initial velocity is down. Therefore, the angle is negative. Again, x unaffected. We can decompose V naught by V naught x, V naught y, but here, so V naught x will still be V naught cosine theta, and even if theta is negative, we don't care, because cosine of a negative number is the same as cosine of a positive number, by property of the cosine. But V naught y will now become negative sine theta. And usually that's what people do. They put the negative sign directly into their equation, and after they do this, they consider only the absolute value of theta. Don't do it twice, otherwise you double dip. Okay, is that clear for everybody? How the initial velocity needs to be checked based on the value of theta? Excellent, excellent. So, now let's revisit the same problem, except our plane is not straight, but is inclined. But we're still going to shoot, as usual, with an angle theta defined from the horizontal. Same problem, except now we're not going to land at A, which is the apogee, nor at B anymore. We're going to land at C. So because of that segment BC, we obviously lost the symmetry. There's 2 methods to solve for this problem. For example, getting the range. There is the pre-calc method, which relies exclusively on Math 135, which is usually what people do. And there is a calculus method, which some people do if they are familiar with their basic calculus 1, which implies rederiving the equation of motion, which seems longer at first, but will actually end up being a way faster method. So let's look at the pre-calc first. We're looking for that distance r, the range. So how far does the ball land? The way to tackle this problem is to realize, okay, my coordinate system is the usual. X horizontal, Y vertical. The trick is to realize, whoa, point C, which is the point of interest. Really, if I'm looking for the range, all I need to figure out is the component of C. If I know xc or yc, I'm good to go. As everybody agrees, due to trig. If you know the x component of c, which is this, and you know the y component of c, which is that, then we're back to a right angle triangle. Pythagoras will allow us to say, well, if I take my y component yc, I square it, and I take my x component of c and I square it, I add out the two, I take the square root, bang, I got my hypotenuse, which is my range. Yeah? So far so good? Okay, so really, once we get those two, we get our r. How are we going to get those two, x and y? One approach is to realize and identify the fact that this is simply a math 135 question. We have two functions, f1 and f2. f1 is the actual trajectory, and f2 is this straight line. And we notice the fact that f1 and f2 intersect at the point of interest. So, if you refresh yourself from high school algebra, if you're interested in a point that lies at the intersection of two functions, and you were looking for its x and its y components, what do? Excellent. Almost, not to zero, but to each other. Perfect. And that's it. So really, it's a math problem. It's a high school problem. All you have to do is set f1 is equal to f2. Those are both function of x. And as you do this, you're going to get xc. Right? Once you know fc, you can substitute either back into f1x or f2x, and bang, you got yc, which now allows you to use Pythagorean theorem and get the r. So very simple. Just the trick was just to identify that point C is the point of interest, which happens to lie at the intersection of two functions. And we know that to get information about that point, all we need to do is equate those two functions. Done. So really what we have to do is figure out f1 and f2. Excellent question, Harry. That's the next step. We need to figure out those two buggers. Let's start with the easy one, f2. f2 is what kind of function? Is it a straight line? Is it a parabola? Is it an exponential? Yeah, it's linear, it's a line. So it cannot be that hard, right? We know that f2 looks like mx plus b. So we need to figure out m and b. Look at your coordinate system and the origin. What must be the value of b, which is the y-intercept, as you look at your diagram and the position of your coordinate system? Yeah, done. Yeehaw! So really, we don't have to worry about m. Perfect. And thank you, Michael. We know that m is negative because we're below. How can we use alpha to figure out the slope? Go back to the definition of slope. Let me use another board. What I'm going to do is I'm going to zoom into the departing point. We want the equation of this. And we know it's negative blah blah times x. Excellent, Alan. We're looking for the slope, and we know that the definition of slope is y over rise. Rise over run, or whatever you learn it. So an easy trick is to just imagine a circle. Unit circle. You're looking for the slope. Therefore, you're going to pick the rise over the run. Again, right angle triangle. This is one unit circle. You need to figure out the y divided by the x. What is the y equal to using trig last week? if you imagine that unit circle. The hypotenuse is 1 because it's a unit circle. You know the angle alpha, and you're looking for this. Basic vector section A and B. What is y equal to? Y is the opposite, therefore sine. Excellent. And the hypotenuse is 1. 1 times sine. 1 times cosine. Correct? So that's just basic vector application. But remember, y is negative, so let's not forget the negative. Therefore, the slope, m, which is y over x, is nothing else but negative tangent alpha. Done. That's the equation of this line. That's simple. Okay? Next one. So we know that this is negative tangent alpha x. What up? Oh, I'm sorry, that was F2. What about F1? Does anybody know how to obtain the functional form of F1, which represents the actual trajectory of our system as is being projected in a longer projectile motion? That is a question that is testing your short-term memory. Because we just saw it 10 minutes ago. From the equation of motion that we know, can we derive the functional form of the trajectory of the system such that time is not involved? So here it's only x and y. Does that ring any bell? Are you referring to equation 5 in this equation, Miguel? Is this representing the equation of y as a function of x? Yeah, this one, right? Equation 6. We just did it. We just derived this before the break and said that this is indeed the equation describes this function as you plot it between x and y, right? Excellent. So that's the one. That's it. We just did it. So let's reuse it. Whoops. Therefore, this function f1 is nothing else but tangent theta. Let's be careful about our angle. Minus g x squared divided by 2 v naught squared cosine squared. That's all we gotta do. And then you solve for x. And that's trivial because x is everywhere. 1 here, 1 here, 2 here. Right? So it's not even quadratic. You can nuke x everywhere, and you only have 1 remaining. So just solve for x. Bang, done. So it's a one-line problem. And then you substitute x into either f2 or f1. I would suggest f2 because it's much simpler. Bang, you got y. And once you get the 2, poof, you get the range. Okay? That's method 1, which is pre-calc. So we need to refresh our high school algebra or functions. The second method, let me use another board. Is to do something we've never done before. Which is that instead of choosing a coordinate system x and y, the standard one, which is x horizontal, y vertical, we're going to rotate our coordinate system. Such that x is along the plane. Why we do this? Because then we know something about point C. In this new coordinate system, what do we know about point C? Excellent. Y is 0, like before, when we had symmetry. Which means that this equation here can be used again. We said y is equal to 0. Remember, that was Allen's suggestion. Now we solve for t, which is trivial, and we substitute here. So we're back to this problem. Bing, bang, boom, easy. The problem is, we can't use that equation. Because you've looked at the lectures, right? And you've seen that those equations are only true if and only if your coordinate system is like this. If you rotate your coordinate system, none of those equations hold. That means you have to rederive those equations. No problem. You practice deriving those equations because you know one of them is going to be in a test. So the only difference is the starting point. A is equal to dv dt. Before, we had ax is equal to 0. We continue from there. And ay is equal to negative g. And we integrate from there. In this case, a little change is that A is still vertically down. Therefore, A has an x component and a y component. This is your ax and this is your ay. Again, we master vectors. Therefore, A is nothing else but, if you know this angle here, which is obviously alpha, then this angle shows up here. Therefore, A is equal to axi plus ayj. Ax is the opposite. Therefore, it will be the sine of the angle, and ay will be the cosine. Now we check the direction. Ax is in the positive direction, therefore it keeps its positive sign. Ay is opposite to your positive y. That's the only change. Which means now that as you derive the equation of motion, ay is equal to dvy over dt, and ax is equal to dvx over dt. Again, remember last time, this was 0. Then we got the equation of motion for x. This was negative g. We got the equation of motion for y. The only change is now ay is negative a cosine alpha. But it's still a constant, so it's no biggie. And ax is not 0. It's a sine alpha. But again, it's still only a constant. And then from there, you can get all the equation of motion. Y as a function of time, x as a function of time, v as a function of time, and v as a function of position. Same old equations. So you can end up with a set of equations will be a little bit different from the one we used to. And as you expect, the only difference really are going to be the acceleration term, which will carry a sine and a cosine. But then once you got those equations, then you can go back to the exact same recipe and method that we use here. Whoops, not here, I guess there. And set your y of that new equation to 0 and use Allen's technique. So feel free to use either or. This is a problem that I like a lot. So please work it out. It is also can be found over and over in at least 100 different places on the archives. So make sure you practice this, because again, hint, hint, this is a problem that I like quite a bit. Okay? Questions? There's a third method I've seen a third method once every couple of years, which is always very clever, but I keep forgetting what it is, and I forget to write it down every time. But you may be one of those who can figure it out. Michael, can you rephrase your question, please? The problem with offset x-axis. What do you mean? Yeah, that one. This is the one I like. I don't know, no worries. So make sure you practice it. There is one like this on the list of problems, right? You've seen it. So make sure you practice it. And the answer is posted. Good, good, good. Any other questions? Okay, so then there is one more I'd like to do. And again, it's on the web, solution is posted, but I just want to go over the starting point. And I believe it is problem number 5, and that's the one. Before we get to problem 5, if you end up, and I'm not sure if there is one of them, maybe problem 8, I would guess, where there's a collision. Yeah. Oh no, problem 8 is the one we just talked about. If there is any other problem that you find on the book or on the website that has two objects colliding, and then another one, and then they collide somewhere, each having their own angle and their own initial velocity. Oh, yes, Michael. Go for it before I get to this type of collision and number 5. Yes, yes, yes. Absolutely. If you have a problem where no schematic or diagram is given, then you have to draw it. You have to make your own diagram. And you have to pick whatever axis that you want, as long as you show it to me, because as we've seen, the axis will be required for you to be able to simplify your equations. Is that what you were asking? Or did I just miss the whole ball? Oh, okay. Yeah, yep. Have you seen any such a problem? Yeah. Ah, okay. Like problem 1, I never give you a diagram. So you have to come up with your own diagram. And then pick whatever coordinate system you want. You will see that problem number 1 is actually, where is it? This problem. That's the reason why I cover this. So this will help you do problem number 1. Oh, oh, bummer. Well, if you're not sure, as you work out those problems, stop by. You know where I am, Kokio202, or take a picture with your phone and send it to me via email, just to be 100% sure. But usually, you are always free to pick whatever coordinate system you like, and therefore, your equation may be simplified and have a different functional form of somebody else who picked a different coordinate system. So as long as you tell me where you put the coordinate system origin and which axis you pick, and those choices are consistent with the functional form of the equation, you can do whatever you want. And this will become even more striking as we do Newton. So yes, it's rare when I enforce a particular method. The goal of this course is for me to give you a method, because physics is not easy. Conceptually, it's very easy. Everybody who listens to lectures from Feynman or whoever, they were like, oh, this sounds cool. This is easy. And it is. But then when they start actually trying to solve problems and use mathematics to solve a particular situation or to make prediction, that's where challenges occur. So that's my role, to give you solid method for all those type of problems, all those concepts, such that if one day you're being faced with a situation that you've never seen before, you know you can always rely on that method. Now, whether you want to use it or not is up to you, or you want to make a variation, it's totally up to you. If you're a non-WI, you can do whatever you want. If you are a WI, I give you no choice. I want you to master that technique regardless. And then in future semester, as you take Physics 272 or C270 or Physics 310, 311, yeah, you can decide to forget about it and do your own thing. But at least you leave this class with a strong background of how to approach physics problems. That's my goal. Okay? So if you're in doubt as you work out any of those problems on the course website, and you're not sure, stop by, or again, take a picture, send it to me via email, and then I'll get back to you in the next day. All right. What was I doing? Collision. If you have a collision problem, that means you are interested in this point of collision, which suggests that you may be interested in its position, x, or y, or the impact, which deals with velocity. How would you approach this problem? Obviously, as usual, you're going to pick a coordinate system. Whatever you want. Just make sure you pick the same coordinate system for both systems. Otherwise, your equation will not be compatible. And then simplify your equations. So you do the same technique. But as you investigate the collision, you want to investigate this point. Let's call it point A. And try to figure out the property of this point. What is like apogee, or when the object is about to hit the ground? What is it that we know between the set of equation of this object, x, y, v, blah, 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 vx, vy, of object, say, O, and object x, oh, not x, object ovaloid, this, so I have two objects, an ellipse and a little ball. What's special at the instant of impact, or at the state of impact, that allows you to relate all those variables with each other? They don't have to collide at apogee. And I apologize, Kyle, my diagram is misleading. In this case, they seem to have happened at collision, but it doesn't have to. So you're going to be facing with a bunch of equations concerning object circle and a bunch of equations concerning object ellipse. How can you relate those equations? Because you have to combine them, right? So we know there is 2 equations for x, 3 for y, so that's 5. So you have 5 equations here, you have 5 equations here, you have 10 equations. Somehow you're going to have to relate them at collision. What will bind them together? Again, I'm sorry, I apologize, Michael, Semascal. This was a misleading diagram. You don't have to have a symmetry. You could have started there, and you don't have to collide at apogee. And if those two are different, which means that the initial velocity is different, theta is different, this initial velocity is different, alpha is different. What else is going to be common to all those equations at point A, at collision? Excellent. The time got to be the same. Does that make sense to everybody? If they both reaches the same state, but at different time, they're going to miss each other. So at this particular point A, the time is the same, which means that the t that shows up in this equation and the t that shows up on this equation are the same. So you can substitute one into the other. And thank you, Dane. The other is, of course, the position. Obviously, if there is collision at point A, both objects, circle and ellipse, have the same position. Therefore, at point A, all the x of this little guy or the y of this little guy are the same as all the x of that guy and the y of that guy. So they share those three kinematic variables in common at collision. They may not share the velocity, neither x or y, because again, v it may be different than v prime, and theta is different from alpha. But for sure, if collision occurs, the time is common between your set of equations, and all your positions are also common. And this is how you're going to relate equations from one another. Okay? So if you're interested in military application or space application, for example, you know, something is being triggered from a random country across a random ocean, and you're trying to figure a way to intercept it, that's all you need. That's all you need. Kinematics. That's it. Of course, there's going to be some little complication because now you have to introduce a third dimension. So you're not dealing with just x and y, but now you have to introduce z. But no biggie. If you can do kinematic in 1D, you can do it in 2D. And 3D is just the same thing. It's just one more equation. And you have to worry about the v naught. Because v naught, we simplify everything by saying, you know, it's an instantaneous velocity you give it. But of course, if it's hypothetically, you know, a little missiles, it will take time to get accelerated. But no problem, that's still engineering, perfectly understood. So you got all the tools in theory here to do such an application. Wonderful. Similarly, if you do space application and you, I don't know, you are on the space station and you like to send them some, you know, food or beer because they're thirsty. It's been like 6 months they're up there. Then you're going to shoot, you know, another satellite that's going to go in orbit, but eventually the satellite needs to be intercepted with the space station. Same thing. For interception to occur, time will be the same, position will be the same. It's like in that movie, which was not very good. Well, I shouldn't say that, which I didn't like that much. It was about space. I forgot what it was. The Martian was pretty good. I liked it. Interstellar, I liked it too. I think it was more recent than what I'm thinking of. But to be honest, now I forget. I heard the Martian book was not good. The way it was written, some students were like, Gravity? Oh, I don't remember which one it was, that one. Maybe, yeah, forget. Hang on. Gravity. Which one is that one? IMDb, Gravity. Whoa, Gravity Falls. Gravity. Oh, 2013. Oh, it could be that one. George Clooney? Oh. The picture rings a bell. I forget. I'm sorry. Brain farts. Anyway, so if you're interested in space application, again, you got all the tools. Well, for space application, you need a little bit more tools. We're going to be needing Newton and energy. But we're going to get there pretty fast. Already Tyson. Oh, was it scary? Oh. I remember Interstellar was trippy. It was the one with different dimension or different time. I forget. That one was pretty good. Lady using space station with realistic physics to go. Ah, maybe that's the one I didn't like, Henry. Then you should present it that way. I figured. Okay. Now, if you are interested in space application and you are interested in going to ME, you need to talk to me or my colleague Aaron Hanai, who's teaching the other Physics 170 and the other C270. He also teaches C271 because we are working with one of the faculty at Manawa from the College of Engineering, who's an ME, who used to work for NASA. He was in the team that sent the first robot that survived and actually landed. I forgot what the name was, on Mars. And then he joined the university. So he's interested in orbital dynamics. That's his thing. And so he's going to come to KCC and give lectures about orbital dynamics to KCC students on a regular basis. And the reason for this is that if you're interested, as you join the team, you get to learn about how to change orbit. That's the type of thing you will learn from him. If you have a satellite in a particular orbit and you need it to change to a different orbit, how do you do this? What is the physics and the mathematics behind it? Or you can apply it to send something to Mars. You put something in orbit, and eventually you need to give it a thrust so that it can jump from the Earth orbit into the Sun's orbit and then the Mars orbit. So different change of orbits. So that's what it does. So if students are interested into this, please let us know. So that next semester, once you have Physics 170 and you're like math, because it's a lot of calculus, then you should join this group. And then as you transfer to Manawa, if you'd like to pursue this type of research as an undergrad, then you get to work with them directly. So that should be fun. It's a class called Site 295. If you're not from KCC, you may not be exposed to this weird little beast. But let me share my screen and tell you a little bit about this. No, that's the wrong screen. I apologize. All right. If you go to this site, for KCC, you will see one class like this. Fortunately, WCC adopted it, HCC adopted it, LCC adopted it, and MAUI adopted it because we have a common grant, but only for engineering so far. At Capirani, we have it for all disciplines. So you can see a research class called Site 25 in biology, if you're interested in doing something in biology, or in botany, or in chemistry, or in computer science, or again in computer science, or in ecology, or in engineering. Yes, I forget there was environmental something, maze mathematics. So all those classes have been created for students who are interested in doing research as undergrad. And this will also give them the opportunity to have this on the transcripts. So as you apply for grad school or for a job, then they can say, dude, I know what I'm doing. I did research under so-and-so, and the topic was blah, 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 blah. And you can pick the topic that you're interested in. And microbiology, they have those downstairs. So for you to join this project, if you're interested in the next semester, you would be asked to, and you most likely will want to take one of those classes. Okay, so you can take it for 1 credit, 2 credits, 3 credits, whatever. And those count as elective in any track of the SNS that you're in. So it's not going to be lost. Not transferable to Manawa, except if you're engineer in some cases, but they will count for your ASNS. So those are cool classes. And they're research class. They're like, $6.99 or when you get your dissertation or whatever. So usually you meet with an instructor once a week and then you do your own thing. Unless it's a hands-on, then you meet with instructor 3 hours a week or something. But usually it's a, it's kind of a directed research kind of thing. So faculty usually treat you like, grad students. So whatever learning you have to do, you do it on your own. And then the faculty is just here to, keep you on the right track. So it's a great learning experience to learn about autonomy and learning stuff by yourself. Oh, yeah, so if you're not in design, well, it depends on the project. I have projects that are programming based. So if it's strictly programming, heck, we can do it online, I don't care. E16 instructor will be joining the project semester. Yeah, Justin is actually going to go back to school and get his PhD and work under the same person. Yes, yes, yes. Yes, yes, yes. He's decided to go back, so that's awesome. Yeah, so it should be fun. It should be fun. And the nice thing about this type of mathematics is that, yes, it is not easy. So be ready to bust up your math and your calculus. But you learn so much. And I'm talking to Aaron, my colleague, who's an ME, so he used to do underwater, which I know nothing about. But then when I look at the stuff they were doing, I was like, come on, guys, that's just physics. Physicists are always arrogant. That's just physics 310, 311, no biggie. So we've been playing with it over the summer. And then as we compare the equation, Aaron was telling me, dude, what you're doing is exactly what we do in underwater robotics. Same type of equations. Doesn't matter. So even if you're not into space-related problem, but you're into underwater robotics, you still can join that topic because the mathematics that you will learn and the skills that you will learn can be applied to underwater robotics as well. So it should be a fun project. But make sure you got your calculus under your belt, and of course your physics. So you have to do good in 170 for you to be able to enjoy that kind of project. Robotic in archaeology? Sure. I mean, robotics can be applied to any STEM disciplines, right? So yeah. Him specifically was robotics for underwater. Now the application of his robot is unknown. I forgot to ask. So I don't know what they use the robot for. Either for archaeology or for marine biology or geology or I don't know. Yay! Atlantis! Oh, Americans know Atlantis? I thought it was like some kind of European bullshit. Huh. Interesting. Okay. Are you referring to my statement, Jamie? Oh, it's a Western. Oh, it's a Disney. Oh, really? Oh, man, I'm getting old. I miss all that stuff. Okay. So, last problem that, 5 minutes, 4 minutes. Okay, last problem I want to lay out the foundation for. And if I miss any of your comments, forgive me, please send again. Meanwhile, there is going to be one problem, which is problem 5, which hopefully you've started to look at, which is going to be a two-step problem. You're going to have a ramp. Again, let's go back to our little hypothetical situation. That's not a superstructure, that's a rocket, which is going to go and then so obviously the ramp is the period of time or space where it's going to have the PC at the end, therefore huge acceleration in this direction. So huge that we're going to neglect for simplicity, but hey, if you want to add it, be my guest. The one due to gravity. And then, as it leaves the ramp, obviously that's now a free-fall project. So now this one is the only one that we consider, because the fuel is going to be exhausted right here, from A to B. And the purpose of the game is to figure out, again, the range, that kind of thing, or the highest points, or whatever. Same questions that we did before. So obviously that looks very similar if you just put your hand over the triangle, right? If you only look at this portion from B to C, you're like, piece of cake, it's just a projectile motion, we just did it, right? You're just going to put your coordinate system wherever you want, but I don't know, most likely you put it here, so that you have x naught and y naught is equal to 0, and then from B to C, just projectile. So really, all you have to do is figure out what's going on from A to B. And for you to be able to complete the projectile, you need to really go after an essential component that shows up in most equations, which is V naught. This angle obviously is the same. So really, you're after V naught, so that you can figure out everything here. And V naught is really the same as VB. So really, you know, after VB. So now you're going to concentrate your attention to this stage. But then you realize, okay, let's imagine that I know this distance, which is my ramp. I start from rest, because my rocket is at rest, and I'm looking for the final velocity. Well, this is just a one-dimensional problem. So you can just identify this problem between A and B. You put your coordinate system right here, another one. This tells you that the initial velocity is 0. You know the distance. You know the acceleration. Bing, bang, boom. You get VB. And then as you go from point B to point C, you realize, well, VB in magnitude is the same as what I used to call my initial velocity. And now you can focus on the right-hand side and do projectile motion. So this is an example of a two-step type of problem. First, you do the 1D between A and B, and you obtain the velocity at point B. And then once you analyze the situation from B to C, you realize, oh, free fall. And projectile motion. So the VB you just calculated is what we used to call V naught in our equation. So it's really just a change of label of two kinematic situations that have a connection at point B. Okay, so please give it a shot. That's problem number 5. It's also a very dear problem to my heart. Okay? So, I'm done with chapter 4, Kinematics2Da. So for next week, remember Monday is a holiday. Thank you for letting me know. I forgot. So 3-day weekend. So on Wednesday next week, we're going to start Newton. Okay? So I will allocate the first hour of Wednesday to answer any question you may have as you complete all those problems on the course website. If there is any challenges or question, bring it up. We'll allocate the first hour to finalize everything. And then the second hour, I will start Newton. And most likely you'll have another surprise, which you might guess what it is, just to make sure that you're on track. And remember this time, as I mentioned in the email, oh wait, I don't want to say too much, otherwise I'm going to give it away. I'm an idiot. Anyway, so it's not really a surprise. I mean, I'm sure you can guess, but that's what's coming. So please complete Kinematics1D2D over the weekend or by Wednesday, and start watching the lecture on Newton on Wednesday, because I'm going to start doing problems right away on the second hour. Okay? So stay ahead of me. Don't fall behind. And then we're going to be ready for the test the following Monday or Tuesday. You will decide. All right. So it's going to be a long weekend. Don't wait until next week Wednesday. If you get stuck, email me. Okay? Take a picture with your fancy phone. If you have one, send it to me via attachment. Circle in red where you got problems and just say, please, fix, or tell me what's wrong. Okay? Don't wait the whole week. Yes, Adrian. I have contacted the testing center in OICC. So I will send you and Trent, I recall, information so you can contact her. But she knows about it, so no problem. Any other questions? Sorry, it's 7:02. I went over time by 2 minutes. If you need to go, please go. And if you have more questions, let me know. Will the next quiz only be on 1D or both? It can be on 1D or definitely on 1D, Dane. And obviously you read my mind. Thank you. There may be one simple question on 2D. But there will definitely still be questions on vector. Okay? So I will always put questions on vector. I don't want you to forget vector. So every quiz, you can have a question on vector for sure. But definitely 1D. Maybe 2D, but if it's a 2D, it's going to be an easy one. Yes, Mabel, I believe I have office hours on Mondays from 4 to 5. So right before class. I didn't grade him yet, Cynthia. He was due last night, I believe. Last night, midnight. And I didn't have time to look at it today, but I'll do it tomorrow. And as soon as I grade them, they're going to be on La Lima. Yep. You're welcome. And Mabel, if my office hours don't, and of course there is office hours from 7:30 to 8:30 here, if people stay. But if the 4 to 5 in face-to-face format is not well with your schedule, no problem. Just email me and tell me, okay, I'm going to be there on Friday. When are you going to be there? And then I can tell you right away, I'm going to be available from this date or this hour, and then poof, we reserve our time. So as long as you tell me a day or two in advance, so that if I have a conflict at the time at which you come, we can find an alternative. No problem. Come anytime. If you are in campus, my door is always open, Monday, Wednesday, Friday. If my door is open, just come in. I don't care about office hours. If my door is closed, then you know I'm busy or I'm not here. Okay, so use that, please, anybody. Excellent. And if you're not on these islands and you don't have the option of coming physically and stopping by anytime you want, please email me anytime. Yeah, my office is a train station. So please use it. There's always people coming in and out. So you're always welcome. Any other questions? All right, you're welcome, Mabel. And I'm sorry, is it Mabel or Mabel? The first one or the second one? I don't want to torture your name. Oh, okay. Sorry, I'm French, so I tend to pronounce the A letter with like A. All right, you're welcome, Tyson. Okay, so let me take a quick smoke break, and then I would like to harass the WI folks. I am having a lack of communication with those folks, and I'm very, very worried. I don't know where you're at, and I know it's not going to be good. So let's talk about all this. Oh, okay. Perfect, Mabel. Okay, so let's meet again in 10 minutes for the WI folks. And if you are not WI but would like to use office hours, please stay until 7:30. The meeting with the WI folks will be short. I just want to play daddy. So feel free to stay. True. True. Okay, see you in 5 minutes.